I imagine everyone is doing well today. I am Mr. Ish. Thank you for joining me. We are looking here at an arc length calculation for the function x squared from a limited domain 0 to 1. It's a seemingly easy function, and it would seem on the surface that this is going to be an easy calculation, but when it comes to arc length, that's not always the case. We have a graph over here from 0 up to 1 domain x squared. You know this right here is an arc. We have to determine the arc length. When it comes to arc length calculations, it's always good to test whether your value in terms of your end result is good. And you can do so by taking a measurement of a straight segment from 0, 0 to 1, 1. I've generated a dotted line, a segment. If I can determine the distance of that by means of the distance formula, you know, y2 minus y1 whole square plus x2 minus x1 whole square, you'll have a 1 square plus 1 square, which is a root 2. 1.414 is going to be the length of that segment. Obviously an arc in terms of a curved line will be larger than this. It should be close to this but larger, simply because the shortest distance between 2 points is a straight line, but a curved line connecting those two will be slightly longer. We are looking here for a rough estimate of root 2. You know it's going to come from 0, 0, 1, 1 equation. It's going to be from 0 to 1. The arc length integral, you have 1 plus dy over dx whole square. If y is equal to x squared, dy over dx is equal to 2x. This is my derivative. It's going to come over here, 2x squared dx. And you complete this, 0 to 1, 1 plus 4x squared dx. Now this right here is a challenging integrand. When we're looking at this integrand, we need to think about a smart substitution, and I'm focusing right over here for my substitution. What if I were to say x is equal to u over 2, hypothetically, and then when I'm squaring this, what would happen? I'll have x squared is equal to u squared over 4. This u squared over 4 coming here can cancel out that 4. So it seems like I'm on the track with this substitution. X is equal to u over 2, and then I can say dx is equal to 1 over 2 du. We will change the limits as would be expected. The limits will be what? u1 and u2. If x is equal to u over 2, you can also say u is equal to 2x. Look right over here for your limits. 2 times 0, well 0. 2 times 1, that's 2. Bring everything here into the integral. You'll have a 0 and you'll have a 2. 1 plus 4x, which is a u over 2 whole square du over 2. Now everything is beginning to take form. Take the 1 over 2 out. I have a 0 to 2, I have a 1 plus 4u square over 4 du. These cancel out, which is exactly what I wanted. 1 over 2, 0 to 2, 1 plus u square du. Now I have something which looks like a square plus x squared, and I'm thinking trigonometric substitution. U is equal to tan theta. Du is equal to secant squared theta d theta, theta 1 and theta 2. Everything with regards to this. 0 and 2. 0 arctan 0. 2 arctan, well it's arctan 2. That's what it is. Now my integral becomes what? It becomes this. And let's put it for you right over here. 1 over 2, 0 arc tan 2. We'll have a 1 plus tan squared theta, and then du is a secant squared theta d theta. You know all of this. This is trigonometric identity, equal to secant theta times secant squared theta. What is it going to become? It'll become a secant cube theta. And that's where things become a little difficult. Secant cube theta d theta. Now I have to think about a secant reduction identity or formula, and I'm going to put that for you right over here. It'll be n minus 2 divided by n minus 1 integral secant n minus 2 theta d theta plus, here n is equal to 3 because I have an exponent 3, plus secant n minus 2 theta tan theta all divided by n minus 1. That's my secant reduction identity. I have a 1 over 2 sitting outside, and I have to do all of this. Secant cube theta being reduced by this is going to give me a 1 over 2 integral secant theta d theta plus secant theta tan theta divided by 2, and you know we still have the arctan 2 and we have a 0. I'm going to put that for you right over here, 0 and arctan 2. You see how things have become a little complicated. An easy function, but everything is becoming complex. because that's arc length calculations. Now we'll open up everything in terms of the parentheses with the antiderivative from here and separation along the positive. 1 over 2 times 1 over 2, 1 over 4. The antiderivative of secant theta, natural log secant theta plus tan theta plus 1 over 2 times 1 over 2 is a 1 over 4 secant theta tan theta, and our antiderivative limits is 0. I'm moving this out of the way, and arc tan 2. What we'll have to do is put the upper limit, the lower limit, and obviously the difference of the two. We will individually evaluate these. Secant of arc tan 2 plus tan of arc tan 2. What's that gonna be? Well, we have to work it out. We can do everything here with the triangle. Theta. My angle theta is represented in terms of a tan 2, which is a 2 over 1. Secant will be over here. What is it going to be? 2, 1, and this will have to be a 5. Secant will be a root 5. We'll have a 1 over 4 natural log. Secant of that angle theta is a root 5 plus tan of that angle is a 2. Now we obviously have to do the minus part of it. It's always the upper limit, the lower limit, and the difference of the two. And we can work on these individually across the positive. I can do this part, upper limit, lower limit, and I can do this part, upper limit, lower limit, and their difference. And now I'll do the parentheses here. 1 over 4 will impact that, natural log. What is everything here with regards to 0 now coming in play? Secant of angle 0 is always a 1. Tan of an angle 0 is always a 0. That's everything here with regards to this expression, upper limit and lower limit. Now let's do everything with regards to this right here. 1 over 4. Secant theta we already know to be a root 5 times tan of that is a 2 minus, we're putting 0 in here, 1 times 0, that's a 0. We have just the task of doing this computation. Natural log of 1, that's a 0. We're going to combine these. Root 5 times 2 divided by 4 plus natural log root 5 plus 2 divided by 4. It's an arduous task, but everything should work out. 5 square root times 2 divided by 4. That's the result here. 1.118 is what I have. Now let's look over here. 5 root plus 2 natural log divided by 4 plus that saved value coming from this side right here, which I'm going to add. I'm getting 1.4789. 1.4789. Now what was our test value? Was equal to 1.414. We are close to it and we are slightly above it, as would be expected for a curved line between 2 points. And this right here brings us to the end of this video. A complex, complicated, arduous task, especially right here. It can get confusing when you're bringing in the previous limits and adjusting them by means of the right triangle trigonometry. It does become difficult. Thank you. Have a good day.